Every second, the Mississippi River is shifting, pushed by gravity. Satellites now track it creeping toward the Atchafalaya, defying decades of engineering. If the river breaks free, New Orleans and Baton Rouge could be left dry, America's supply chain halted, and $1.9 trillion in assets at risk overnight. The story you are about to see reveals why the population should be terrified and what the latest sensor data uncovers that authorities cannot ignore. How close are we to losing control? Time-lapse sequences from Landsat and Sentinel satellites reveal the Mississippi River's restless movement across the Louisiana landscape. Over a series of years, the river's centerline drifts unmistakably westward, inching closer to the Atchafalaya. Displacement vectors superimposed on satellite composites show a persistent migration, arrows stretching from the main channel toward the steeper, shorter route. These vectors measure not just subtle shifts, but a collective force, with some channel margins registering movement in the range of several meters per year. The river's bends, once stable, now appear to flex and reach, their outlines changing between frames. Channel scars and abandoned meanders become more pronounced, tracing the history of past attempts to break free. Sediment plumes, visible as shifting bands of color, reinforce the direction of flow where the river's energy is most concentrated. In the Atchafalaya corridor, the water's path grows more distinct, its outline sharpened by each new satellite pass. The magnitude of these changes is not speculative. It is visible, mapped, and measurable. This is not a static river. The vectors are evidence of ongoing migration, a process unfolding in real time, captured from orbit and rendered undeniable by the precision of modern remote sensing. For the first time, the river's intent is written in data, not just in the scars it leaves behind. Along the levees, a different kind of evidence accumulates. Real-time data logged from the ground, hour by hour, by engineers who know every inch of the river's defenses. Water seepage sensors buried deep in the levee cores register subtle changes in pressure, flagging spots where the river's force is beginning to push through. Tilt meters and settlement gauges track the crest of the levee itself, capturing movements as small as a few millimeters. Over the past year, some sections near Old River have shown a steady downward trend, levee crests settling by as much as 12 millimeters in a single season, far above the background rate. Plots from the latest inspection runs show a pattern. Displacement is not uniform. The greatest movement lines up with bends where the river's pull toward the Atchafalaya is strongest. Engineers compare these in field readings with the satellite data, confirming that the surface shifts visible from orbit are matched by real physical deformation measured on the ground. In one set of logs, seepage rates doubled during the last high water event, forcing emergency sandbagging and 24-hour patrols. Gauge stations at Old River now show small but persistent shifts in water stage, with the main channel's pressure creeping upward each spring. These numbers are more than statistics. They are the river's intentions, recorded in the language of sensors and steel. For the levee board engineers, each spike on a chart is a warning, a sign that the river's push is not just visible from space, but is being felt minute by minute in the earth beneath their boots. At the Old River Control Complex, the U.S. Army Corps of Engineers keeps a constant watch on the river's every move. Live data streams from their dashboard show real-time discharge rates and pressure readings at key points along the system. The Corps' engineers compare these numbers against decades of historical records, looking for any sign of deviation from the expected flow split: 70% down the Mississippi, 30% diverted into the Atchafalaya. When asked about the recent satellite and levee sensor findings, the Corps issues a clear statement: the data is accurate. The measured westward migration, the increased pressure at Old River, the levee settlement, these are not outliers or sensor errors. They reflect real changes in the river's behavior, confirmed by ground truth and agency monitoring. On camera, a Corps engineer points to the dashboard. Every spike, every subtle shift is logged, reviewed, and double-checked. The agency's confidence in these measurements is unwavering. For the Corps, the numbers are not just statistics. They are the basis for every operational decision, every emergency plan. Their validation transforms remote sensing from a scientific curiosity into an operational fact. With this endorsement, the evidence carries the full weight of federal authority. The story now moves from what is seen to why it is happening, as the Corps prepares to explain the natural forces driving the river's restless push toward the Atchafalaya. The Mississippi River's urge to break away isn't just a matter of restlessness, it's basic physics. The Atchafalaya offers a shortcut to the Gulf, slicing 150 miles off the current route. That alone would tempt any river, but the real draw is the slope. Where the Mississippi meanders south from Old River, it loses elevation slowly. The Atchafalaya, in contrast, drops 17 to 19 feet in a much shorter run. Water always seeks the steepest path down, and here, gravity is doing the math. A geomorphologist at Louisiana State University puts it plainly: for a river, the shortest, steepest route wins. The Mississippi's own bed has been rising over time, built up by layers of silt and sand carried from nearly half the continent. Every flood season, that bed creeps higher, pushing the river surface up and increasing the pressure difference between the Mississippi and the Atchafalaya. The greater the drop, the more energy the river has to spend, and the more it wants to spend it quickly. Measured in raw energy, the Atchafalaya route is a gravitational bargain. For every foot of drop, the river can move more water, faster with less resistance. That's why the channel migration isn't random. It's the river following the path of least effort, guided by geometry and the pull of gravity. The numbers show a system on the edge, where even a small increase in gradient can tip the balance. This physical advantage is the engine behind the river's persistent push west, setting up the next chapter. What happens when all that energy meets the sediment load carried from the heart of America? Sediment from 41% of the continental United States pours into the Mississippi each year, carrying silt, sand, and clay from as far away as Montana and Pennsylvania. This material does not just ride along quietly, it reshapes the riverbed, raising it higher with every flood season. Each time the river overtops its banks or surges against the levees, it scours the channel, carving deeper paths where the current is fastest and dumping fresh layers of sediment where the flow slows. The result is a self-reinforcing cycle. As the bed rises, the river's surface climbs, increasing the pressure difference between the Mississippi and the Atchafalaya. That pressure drives more water toward the shortcut, deepening the Atchafalaya channel and making it even more attractive as an escape route. Recent floods have accelerated this feedback. In 2011 and 2019, record volumes thundered through the system, stripping sediment from the Mississippi's banks and gouging the Atchafalaya's bed. The more the river floods, the more it undermines its own defenses. LSU geomorphologists describe this as a runaway process. Each flood season does not just move water, it moves the odds. The river is not just restless, it is actively amplifying the forces that pull it west, setting up a contest between sediment, gravity, and the structures built to hold them back. Probability is the language of risk, and when it comes to the Mississippi's future, even the most advanced models tread carefully. The U.S. Geological Survey and the Army Corps of Engineers run scenario analyses, feeding in everything from channel migration rates to levee settlement logs. Their models simulate thousands of possible futures, but the outputs are sobering in their uncertainty. No agency will put a hard number on the odds of catastrophic river revulsion in the next year, or even the next decade. What they do say is this: the long-term recurrence interval for a natural course shift is between 800 and 1,200 years, a figure drawn from centuries of sediment records and delta history. That translates to an annual probability well below 1%, comforting on paper, but less so when considering that engineered controls now carry the burden of holding back a process that is, by nature, overdue. U.S. Geological Survey hydrologists point to a range of qualitative risk bands rather than fixed numbers. Models show that the chance of a major course change remains low in the immediate term, but grows with every year of levee stress, every record flood, and every millimeter of settlement at Old River. The color-coded outputs, green for status quo, yellow for increased migration, red for catastrophic capture, don't offer certainty, only a shifting window of vulnerability. In one model, the probability of a major event climbs from under 2% in a single year to as high as 14% over a decade, depending on the scenario. But every analyst cautions, these are not forecasts, just boundaries for what is possible. The only consensus is that the risk is real, rising, and impossible to ignore. In 1927, the Mississippi River unleashed the most destructive flood in American history. Entire towns vanished beneath the water, and the disaster forced the federal government to rethink its approach to flood control. Out of that reckoning came a new philosophy. The river could be contained, not just by levees, but by engineered intervention. Decades later, as the Atchafalaya began capturing more of the Mississippi's flow, engineers faced a deadline. By 1953, Corps hydrologists warned that without action, the river would shift course by 1990. Congress responded by authorizing the Old River Control Structure, a concrete and steel barrier completed in 1963 at the critical juncture north of Baton Rouge. Its mission was straightforward: maintain a 70-30 split, keeping most of the Mississippi flowing toward Baton Rouge and New Orleans, and only a controlled share down the Atchafalaya. For a decade, the system held steady, but in 1973, record floods put the structure to the test. Turbulent water collapsed a 67-foot wing wall, scoured out the foundation, and left steel pilings exposed. 7 of 11 gates were nearly undermined. Engineers scrambled to shore up the damage, pumping cement grout into the voids beneath the structure and racing to construct emergency stone dikes. The Morganza floodway was opened with little warning to relieve pressure. The crisis left permanent scars. The original safety margin was slashed, with the maximum safe waterhead reduced from 37 feet to just 22 feet. The structure survived, but only by a narrow margin. In the years that followed, the Corps launched an 8-year rehabilitation program, finishing upgrades in 1981. By 1986, an auxiliary structure was added to share the load. Yet each modification was a reminder: the system's margin for error is slim. Today, the Old River Control Complex stands as a patchwork of original engineering, emergency fixes, and hard-won upgrades. The river's pressure never relents, and the line between control and catastrophe has grown thin. As one Corps officer puts it, every high water season is a test, and the room for mistakes has all but vanished. Cargo ships queue along the lower Mississippi, their hulls loaded with grain, fuel, and chemicals bound for every corner of the globe. The Port of New Orleans, ranked among the busiest in North America, moves hundreds of millions of tons each year: grains from the Midwest, chemicals from the Gulf refineries, steel, coffee, and rubber. Just upriver, the Port of Greater Baton Rouge handles fertilizer, petroleum, and bulk cargo, connecting the heartland to the world market. Together, these two ports anchor a supply chain valued at nearly $1.9 trillion annually, according to recent asset overlays and economic impact studies. That figure covers not just the cargo, but the refineries, grain elevators, and distribution centers that depend on a navigable river. A port director standing beside a wall of tracking monitors describes the daily stakes. Every barge that arrives carries a contract, a deadline, and a ripple effect. If the river's flow falters or shifts, ships cannot reach their berths. Grain sits idle on the levee, fuel shipments stall, and global buyers start calling for answers. The port's maps show more than shipping lanes. They chart the arteries of the national economy. A sudden course change would leave docks high and dry, with navigation channels silted in and freshwater intakes exposed to saltwater. The overlay analysis reveals the dense web of assets that depend on the river's current path. Terminals, pipelines, storage tanks, and water plants, all mapped in red zones of risk. The numbers are not abstract. They translate to jobs, contracts, and supply chains that stretch from Iowa to Indonesia. A single interruption would send shockwaves through food prices, fuel supply, and export markets. For the port directors and logistics teams, the river is not just water. It is the backbone of an economic system that cannot afford a sudden break. In the Atchafalaya Basin, the river's choices are not just lines on a map, they are the difference between home and exile for entire communities. Wetlands that once stretched unbroken to the horizon now vanish at the rate of a football field every hour. As the river's sediment skips past the old delta, the marshes near New Orleans shrink, starved of the mud and fresh water that built them. Saltwater pushes farther inland with every dry season, creeping up abandoned bayous and into municipal water supplies. In Morgan City, a terminal operator describes watching the tides grow stronger and the taste of the tap water change. Fishermen in the basin face new uncertainty with each season. Shrimp and crawfish nurseries depend on a delicate balance of fresh and brackish water. A sudden shift in the river's course could turn their marshes into open salt water in weeks. Generations of families, whose livelihoods trace back to the earliest days of settlement, now weigh whether to invest in new boats or prepare to leave altogether. John McPhee once wrote that in this part of Louisiana, people live with the river's power as a fact of daily life, not a distant threat. Today, that fact is changing. The chain reaction set off by a course change would not stop at the water's edge. Coastal loss would accelerate, storm surges would reach farther, and towns built on the promise of the river would face the reality of its absence. The story of the Mississippi is written in these communities, a reminder that the numbers on a risk map translate to real families, real homes, and a future that grows more uncertain by the year. Interferometric synthetic aperture radar, INSAR, now tracks the Mississippi's every move, measuring levee shifts down to the millimeter. Sentinel-1 satellites sweep the region every 6 to 12 days, building a time series that flags even the smallest ground deformation. Paired with real-time logs from tilt meters and seepage sensors, this network forms a virtual tripwire for the river's next move. When a sensor crosses a set threshold, engineers receive alerts within minutes, triggering field checks before a minor disturbance can escalate. Policy analysts reviewing these systems point to their reliability. The technology is not just theoretical. Upgrades in the last 5 years have doubled the number of monitored sites along vulnerable levee stretches, and new protocols ensure that detected anomalies prompt immediate reinforcement. This approach, constant surveillance, rapid response, and targeted fortification, offers a proven way to stay ahead of the river's pressure, buying time for larger decisions. As one analyst puts it, the tools exist. The challenge is keeping pace with a river that never sleeps. 3 decisions stand at the threshold. First, expand real-time monitoring. Accelerate satellite analytics, double ground sensors, and demand instant alerts for every sign of levee displacement or channel shift. Second, commission a national risk review. Bring together engineers, economists, and emergency planners to quantify the true cost and feasibility of each path. Manage diversion, phased relocation, or contingency-only defense. Third, launch flexible, scenario-based infrastructure planning. Identify critical water, port, and supply nodes that must survive any future, and start building redundancy now. Managed diversion buys time, but requires decades of coordinated transition. Planned relocation means investing before disaster strikes, not after. Contingency response alone is a gamble, one that risks trillions if the river wins. The clock is running. Every year of delay narrows the margin for action. Right now, satellites and sensors capture a river straining against human control, while aging infrastructure stands as our fragile line of defense. Every season adds urgency as climate extremes rise, and there is no modern precedent for a course shift of this scale. The future of millions hinges on choices made before nature makes its own. The Mississippi is not waiting for permission, it is moving.